Hello and welcome to Empowered Learning. This video will be about evaluating the limits of a function algebraically. That means doing it computationally versus looking at a graph and figuring out the behavior of that function by that means. So to be able to do this, there's a few things that you have to know before we begin. The first thing that you have to know is some of the basic limit laws. If you do not know those, you may want to review those before actually looking at this video. The second thing that we need to know is the fact, and whenever we are evaluating a limit, we're talking about the behavior of a function, and a lot of times we're trying to find the behavior of a function around an x value where the function is not defined or is not continuous set. So we need to make sure that we have that perspective as we start to evaluate these limits here. Now, one thing that we want to also keep in mind is that if for our function, if we take the limit of it and the x value that we're trying to take the limit of from both the left and the right is in the domain of the function, then unless there's some kind of jump discontinuity going on there, we will be able to just plug in that particular x value and figure out what the limit is. And so another way of me saying that is that if my function is continuous at that particular x value, then we can literally just plug in the x value and figure out what the answer is. But in most cases, we're not going to be able to do that directly. So we have to rewrite our function in a certain way to be able to get it in a form to where we can do that. And so as I go through these, I will not only be evaluating the limits, but I'll also be interpreting what that actually means graphically. All right, so for our first problem here, this asks us for what is going to be the limit of this rational function as x approaches 2 from both the left and the right. We can interpret that as saying we want to know the behavior of this particular rational function as x approaches 2 from both the left and the right. Now, one thing that we know about rational functions themselves is that rational functions have discontinuities in two different cases. One case is we have vertical asymptotes, and another case is we have holes, or some textbooks call them removable discontinuities. And so, of course, we need to figure out, does this particular rational function either have a vertical asymptote at x equals 2, or does it have a hole at x equals 2? How we're going to go about finding that out is, as of right now, if we were to take 2 and just plug it into x everywhere where we see it, we would eventually get some number being divided by 0, which is undefined. And for this situation here, it's not really telling us anything. So, and I think in this case we actually get 0 divided by 0, which really doesn't tell us anything because in calculus that's actually an indeterminate form. So what we need to do is rewrite this function in a way to where we can actually see what's going on. So I'm going to erase all of this, and we'll start off just by trying to factor the numerator, since the denominator doesn't have much to work with. So we'll see here that this is x plus, x minus, and the factors of 6 are 2 and 3. And since we need a positive number in between here, we'll put 3 here and 2 there. And if we do the FOIL method on the numerator, we'll see that it checks out to be x squared plus x minus 6. And so here you see that we have x plus 2 as a common factor in numerator and denominator. So here that will reduce to 1, but it will reduce to 1 with the understanding that x cannot be equal to 2, which implies here there is a hole located at x equals 2. And so this kind of knowledge actually comes from pre-calculus or college algebra, depending upon what course or courses you took. So in essence, what this means here, now that we've taken our rational function and simplified it, what we're actually saying is that this particular function is acting just like this one, but this particular function here act like this one, but have a hole at x equals 2. And so when we evaluate the limit of this, what we're saying is the behavior of this function is going to act just like the behavior of this function. And so now at this point, we see that the function x plus 3 is just a line, which is like a polynomial of degree 1. And 2 is in the domain of that, because if I plug in 2, that is a real number, and I sub it in for x, the result that I get out is also a real number. So because of that, we can use a property called a direct substitution property that allows us to be able to just plug in 2 in for x, and we see that the limit of this particular function is 5. And what we're actually saying here is that our function, if let's say if we call this f of x, we're saying that f of x has a hole at the point 2, 5 in its graph. Okay. All right, so let's look at the next example here. So just like how we did example A, what we need to do is rewrite this function. And mainly what we'll do is factor the numerator and denominator to do that. So if you notice, I'm taking the function that's inside the limit and simplifying it first. And then after that, I start writing my limit notation. And I'm doing it this way to be notation-wise, to be correct, but at the same time to keep from having to write limit as x approaches 2 a whole bunch of times. Because if you don't kind of separate your work here and do it like how I did up here, you're going to have to do limit as, in this case, x approaches 2 a whole bunch of times. So that's the reason why I'm putting the semicolon here, and I'm kind of working on this separately. All right, so for here, we know that the numerator factors out the t minus 3 times t plus 3. Let me get a little separation here. And the denominator, that will factor out. I have 2t here and t there. Since we got plus and plus here, it'll be plus and plus there. And the factors of 3 is just 3 and 1. And if we multiply 2t times 3, we get 6t, plus 1 more t is 7t. So this works out. Again, we see the case where we have a common factor in numerator and denominator. So that means these factors will reduce to 1. And what we have left is t minus 3 over 2t plus 1. And again, what we're saying is that this function, the one that we started off with, is going to act just like this function t minus 3 divided by 2t plus 1. But we know that t is not allowed to equal to negative 3. And put another way, we're saying that there is a hole located at t equals negative 3. And so now when we evaluate the limit, we're actually just going to find out what the y value or y coordinate is for that hole. So coming back here, we say the limit of this function as t approaches negative 3 from both the left and the right, what will be just like saying the limit of this function. And here we know that negative 3 is in the domain of this function, because if I plug in negative 3 in the denominator, I am not going to get 0 as a result. So here I can use direct substitution property and substitute that in directly. And then I'll get negative 6 in the numerator and 2 times a negative 3 is negative 6 plus 1, and that ends up being a positive 6 over 5 because negative divided by negative is a positive. And so what this implies here is that at negative 3 6/5 is where your hole is. So the answer to the question is this, but the interpretation of it is that we know that this particular rational function has a hole at the point negative 3 6/5 on this graph. All right, so let's move on to some other examples. All right, so in our next example here, we're going to do the same thing. We're dealing with another rational function here. So let's see how we can take this function and break it down, or factor it out, or simplify it. So one of the things that we recognize here is that in the denominator, this is going to be the sum of 2 cubes. And so in general, whenever we factor out the sum of 2 cubes, it's going to be a plus b times a squared minus ab plus b squared. Okay. Now, if we had the difference of 2 cubes, and this is just for general information here, it will factor to a minus b times a squared plus ab plus b squared. And let me make that like that. So in this case, we know that we're going to use the sum of 2 cubes, and in this case, our a is going to be x, and our b is going to be 2. So when we factor that out, this will just be x plus 2, x squared minus 2x, and then plus 2 squared. So then from there, we see that we have a common factor of x plus 2. So that will reduce to 1, and that's letting us know that this rational function will act just like this one. And of course, here we know that the interpretation of this is that we have a hole located at x equals negative 2. And again, what I mean by located is that we're saying, hey, this is the x value for where this happens. We're not talking about the actual point yet, because we need to evaluate the limit to figure out what the point is. So now that we kind of know what's going on, we can finish this problem. So I'm just going to go ahead and erase what I have here. Go ahead and put that back in. And so now, here we know that the limit as x approaches negative 2 of our original problem is going to be the same as the limit as x approaches negative 2 from both the left and the right of 1 over x squared minus 2x plus 4. And if we look here, negative 2 is in the domain of this function, because if I plug in a negative 2 in for x, I am not going to get 0 in the denominator. So here, just literally plug in negative 2 everywhere where I see x. And the result that I'm going to get here is 1 over 12. Just do some little separation there. So negative 2 squared is 4. Negative 2 times negative 2 is 4. And we got plus 4. So all that adds up to be 12. So the answer to this question is 1/12, but the interpretation of it is that, and we'll call this function f of x. So f of x has a hole at the point negative 2, 1/12 on its graph. All right, so moving on to example D. What example D is actually doing is actually a form of the difference quotient. And so if we look at this, if I, let's say, rewrote this as 2 plus h raised to the 3, then what I'm actually doing here is I'm saying what is going to be the limit of the difference quotient of some function here, where the function itself is x cubed, and the x value that I want to find out the derivative of at a particular x value is going to be at 2. So that's literally what this is doing. So if I was to draw what's going on, we have this function here, x cubed. And so here at the point 2, 8, what we're really trying to do is find out what the slope of the tangent line is that goes through that point. That's literally what this is telling us to do. Okay? But for right now, all we're going to do is just evaluate the limit straight up and not worry about the interpretation of it here. But for those of you that are interested, that's actually what's going on. All right, so to be able to do this problem, we need to figure out an easier way to write h plus 2 quantities cubed minus 8, all that divided by h. And so first thing that we need to do is expand out this h plus 2 quantity cubed. And so one way that we can do that is by binomial expansion. But I understand that some people may not be familiar with that, so I'm going to purposely do this the long way so that everyone can follow me. So here, I'm just going to start off with h plus 2 quantity cubed, which is like multiplying h plus 2 times itself 3 times. Okay. And so for the first 2, we'll multiply those together using the FOIL method, and it will be h squared plus 2h plus another 2h plus 4. And of course, all of that is just multiplied by h plus 2. And then this will simplify to h squared plus 4h plus 4. And all that multiplied by h plus 2. And now we'll do convolution, basically taking h and multiplying it to all 3 terms, and then taking the 2, multiplying it to all 3 terms, and then combining like terms. So if we multiply all 3 terms by h first, and that'll give us h cubed plus 4h squared plus 4h. And then we multiply everything by 2, be 2h squared plus 8h plus 8. And then we'll go ahead and combine like terms. So I have h cubed, we have the 4h squared, and the 2h squared combines to be 6h squared. We have 4h and 8h combined to be 12h, and then we just have 8. So we know that this first part here is just going to be this h plus 2 quantity cubed is just going to be what we have here. So I'm going to go ahead and erase all this other stuff and just write what the end result is. So I'll go ahead and erase all of this. And so we know here that h plus 2 cubed is just going to be all this information here. So I'll just erase all that and rewrite it. So let's see, h cubed plus 6h squared plus 12h plus 8. And we'll just get rid of all of this down here. All right, so now that we know that, then of course h plus 2 quantity cubed minus 8 is just going to be h cubed plus 6h plus 12h plus 8, and then minus 8. So that's going to cancel. And now we just have h cubed plus 6h squared plus 12h. So now we can actually come and figure out this limit here. So the limit as h approaches 0 of what we have in here will be the same as saying the limit of h cubed plus 6h squared plus 12h, all of that divided by h. And of course here, we can factor out an h out of all the terms in the numerator. And that'll leave us with h times, in parentheses, h squared plus 6h plus 12. These h's will reduce to 1. And what we have left is just the limit as h approaches 0 of h squared plus 6h plus 12. And at this point, we know that if we plug in 0 for h, this will h will be in the domain of this function, because we won't get anything that's undefined. So we just have 0 squared plus 6 times 0 plus 12, which will give us 12. And so the answer to this limit would be 12. The interpretation of it will be for my function f of x, which is x cubed, at the point 2, 8, the slope of the tangent line that goes through the point 2, 8 will have a slope of 12. That's literally what we did here for example D. All right, so looking at example E, different limit, same situation. We need to find a way to be able to rewrite what we have inside of here. So what I'm going to do is, I realize that this is a rational function just written in a crazy kind of form here. So what I'm going to do to make things easier is I am going to multiply the numerator and denominator of this particular function by the LCD of all of the denominators. And so in this case, my LCD will end up being just 4x times 4 plus x. So when I come here and do 1/4 plus 1 over x, 4 plus x, we're going to multiply numerator and denominator by all of this. And what this will do is help us get rid of the fractions here relatively quickly. So if we go and multiply 4x times 4 plus x to the first term here, what we'll get is 4x times 4 plus x in parentheses all over 4, plus we would get 4x times 4 plus x in parentheses all over x. And of course in the denominator, this would be just 4 plus x here, and then this is times 4x, 4 plus x, like that. All right, continuing on, as you can see here, we have these 4's that will reduce to 1. And all we have left here is just x times 4 plus x. In the second term, we have x's that reduce to 1. And all we have left is 4 times 4 plus x. And in our denominator, we just have 4x times 4 plus x times 4 plus x. And so here we see that we have in common a 4 plus x in the numerator, so we factor that out, and we just have x plus 4 remaining. We write the denominator, and we note here that 4 plus x is the same as x plus 4. So here we have those 4 plus x's reducing to 1. And it's also reducing to 1. And what we have left is just 1 divided by 4x. So what this means is that now the limit as x approaches -4 of what we started off with is behaving just like the function 1 over 4x. And since when we plug in -4 into the function, it does not give us a denominator of 0, we know that -4 is in the domain of this function, 1 divided by 4x. So we can just substitute it in. And our answer ends up being 1/16. And so again, like we've seen before here, whenever we had common factor in numerator and denominator, what that has communicated to us is that we have a hole in our graph. So what this means here is that we have a hole in the graph at the point -4, -1/16. So in the language of calculus, that's what that's saying. So let's move on to the next example. All right, so for this example, very similar to the one that we did before in example E. What's different about it is now we have things written instead of 1 over something as that same thing raised to the -1. So we note that anything that's raised to a negative exponent can be rewritten this way. So here we're going to rewrite what we have as 1 over 3 plus h minus 1/3 all over h. And so this time we're going to do the same thing as we did last time. And we are going to multiply numerator and denominator by the LCD. This time I'm going to make it a little easier and just multiply it times the LCD of just the numerators here. Because if we saw in the last problem, we actually had a double factor of x plus 4. And so we really didn't need that. So I'm going to simplify this and just multiply numerator and denominator by the LCD of the numerator, which is just 3 times 3 plus h. And so if we do that, of course, in the first term, we'll have 3 times 3 plus h, all that divided by 3 plus h. In the second term, we'll have 3 times 3 plus h, all that divided by 3, and then everything divided by h. And so here we see that we have the 3 plus h's that are common, so we reduce that to 1, and we just have 3. Minus, and then here we have 3's that are common, so we reduce that to 1, and what we have left is 3 plus h in parentheses. And it's important that you put it in parentheses here. And all that divided by h. Now, to get to our next step, we distribute our understood -1 here for our subtraction to both terms. Looks like, oh yeah, I lost something here. Sorry, y'all. Yeah, so this should be h times 3 times 3 plus h. Yeah, I forgot to write that. So I'll go ahead and write it here. So that will be again h times 3 plus h. And that'll just be 3h, 3 plus h. All right, sorry about that. So now when we simplify the numerator, we know that 3 minus 3 is 0, so that cancels. And we just have minus h in the numerator. We have 3 times h times 3 plus h in the denominator. And here we see that these h's reduce to 1. So what we have left is a -1 in the numerator and 3 times 3 plus h in the denominator. Let's get that 3 looking good here. So now we know that if we come back here, the limit as h approaches 0 of what we originally had is going to act or behave the same way as -1 over 3 times 3 plus h. And again, if we plug in 0 into this function, we see that it won't give us a denominator of 0. So 0 is in the domain of it. And our final answer here is -1/9. And of course, this interprets to, here, if we were kind of looking at this as a function, we would say, hey, we have a hole at the point 0, -1/9. But what we're actually doing here is looking at a function of 1 over x, and what we're trying to do is figure out what is the derivative of that function at x equals 3, or put another way, what is the slope of the tangent line of this particular function, 1 over x, when x is equal to 3. And if we look at that, 1 over x looks like this. When x is 3, we're here. Here's this point. And so the tangent line will look like this. And of course, that line is going down from left to right, so it's negative. So it makes sense that our answer here is -1/9. All right, so for our next example, we see that we're dealing with something a little different here. We have x plus 3 divided by absolute value of x plus 3, and we are trying to figure out what is the limit or the behavior of the function as x approaches -3 from both the left and the right. Now, one way that we could do this is we could actually define this as a piecewise function, and I say that because of the absolute value part. So in general, whenever we talk about the absolute value of a function, we're talking about the distance of it. But when we define this as a piecewise function, it would be defined as follows. So we know that absolute value of x will just be the same thing as x if x is a non-negative number. And it'll be the negative of x if x is a negative number. Or put another way, the absolute value of -2 is 2. Or if we think about it in terms of how we define this piecewise function, since -2 is less than 0, this would be the negative of -2, which is just 2. Absolute value of 2 is just itself 2, because 2 is a number that's greater than or equal to 0. Okay? So because of that, I can now say the absolute value of x plus 3 is defined as x plus 3, and this will be for all values of x that will be greater than or equal to -3, because of course plugging in -3 here would make this expression x plus 3 here be 0. And this will be also negative of x plus 3 if these values here are less than -3. Okay? So combining that, if we were to actually define what x plus 3 divided by absolute value of x plus 3 is, this would be defined as follows. It would be x plus 3 divided by x plus 3 for all values of x that are greater than -3. Okay? And I'm not doing greater than or equal to, because if I say equal to and I plug in -3 in the denominator, I'm going to get 0, which I know I can't have. Now, in the instance of when x is less than -3, this will be x plus 3 divided by the negative of x plus 3. Okay? And that's for all values of x that are less than -3. Now, the last part of this, I'm going to move this down so that we can see the rest of this. So the last part here is we know that this is going to be undefined when x is actually equal to -3. Because if I was to plug in -3 in for x into here, this is what I would get. And 0 divided by 0, contrary to popular belief, is not 0. it is undefined. It's an indeterminate form. Okay. So now if we simplify everything, what we see is just x plus 3 divided by itself is just 1. X plus 3 divided by negative x plus 3 is negative 1. And then, of course, we have undefined here. So if we were to evaluate the limit of this function, we would see just from the behavior of it, the answer to this would be does not exist. And so I'm going to erase some of this to show you why that would be. So if we were to actually draw what we have here as a result, the graph would look something like this. So we know all the action is happening around x equals negative 3, and we know that here this would be value of 1, value of negative 1. As long as x is greater than negative 3, then we have a horizontal line that looks like this. If it's less than negative 3, then it looks like this. And of course, it's undefined right at x equals 3. Now, remember that anytime we ask for the limit of a function, what we're actually asking for is what is the behavior of this function as x approaches this number from both the left and the right. As you can see, the y values approach negative 1 to the left of negative 3, and they approach positive 1 from the right of 3. And so in order for us to be able to answer this limit with a real number, what we have to have is the function approaching the same y value from both the left and the right. And since it doesn't, then we know that this particular limit does not exist, meaning that the behavior of the function x plus 3 divided by absolute value of x plus 3 does not consistently approach the same y values from both the left and the right. Okay, so that's how we work this particular problem. Now let's move on to the last example. So for this example, we notice that we also have this absolute value function here. But one of the things that I want you to notice is that we have this absolute value function, but we are trying to approach x equals 5 from both the left and the right. Okay. Now, for values that are closely around 5, so for instance, I'm going to say like 4.9, 5.1. Okay. If I was to plug in 4.9 into this absolute value, I would get a positive number, namely 0.9. If I did the same thing for, let's say, 5.1, of course, 5.1 minus 4 would still give me a positive number. So because of that, in this instance, since all the numbers that are closely around 5 are going to produce just positive numbers inside of this absolute value sign, we could actually rewrite this limit this way. And effectively, what I'm doing is just dropping the absolute value signs, because I know that absolute value of x plus 4, remember that's going to equal, x minus 4 is going to be x minus 4 for all values of x that are greater than or equal to 4. And since 5 is greater than 4, we could just simplify it to just this. And so now from here, if I take 5 and I try to plug it into the x in the denominator, I know that I'm not going to get 0. So I know that 5 is in the domain of it. So literally, by direct substitution property, I can just plug in this x value here. And this would just be 3 times 1 over 10 minus 8. And we end up getting 3 over 2 as an answer there. And so what we're saying in this case is that for this function here, we're saying that this function is continuous at x equals 5, and that it literally has the point 5, 3/2 on its graph. And so this will conclude the examples on evaluating limits algebraically. I hope this has helped. If you have any other examples that you're wondering about, just please send them to me, and I'll get to them as fast as I can. Thanks so much.